All right, so in this video, we're going to continue introducing logical operations, which are also sometimes called logical connectives. And in this video, we're going to go over some of the binary operations, which take two inputs, combine them, and produce one output. This produces what are called compound propositions, which are essentially logical propositions that are built by combining other propositions using operations. So, I've got the beginnings of a truth table here. We're going to build a big truth table, and we're going to have a column for each of the propositions. So in order for us to build a truth table, we're going to, for binary operations, we're going to need two inputs. So I've got my inputs written over here. These are my inputs. I'll label those. They are P and Q. Now, before we get started, we need to write down all of the possible combinations of values for P and Q. And actually, there's sort of a systematic way to figure out what that is. And this method I'm going to show you here extends to any number of variables. It's called the lexicographic ordering. Let me spell that. Lexicographic ordering, or just order. That comes from the word lexicon, which has to do with books and libraries. So it's basically alphabetical order is what it is. It's exactly alphabetical order. But applied to like some other scheme. So in this case, with trues and falses, we can say let's have trues first and falses second. Just like having A and B, the very first word in the alphabet would be AA, right? If it's combinations of two letters, the first one alphabetically would be AA. So our first one is going to be true, true. The next possible combination in the written in alphabetical order would be AB, right? So that would be true, false. Then we move on to saying, okay, what if it starts with a B, right? BA would come before BB. So the next one would be false, true. And then lastly, we'll have false, false. So there we go. We're going to have 4 rows in our truth table. There are 4 different combinations of truth values for these two variables. I'm just going to real quick give myself some nice rows here. Oops, that was a little narrow on the end there. It's fine. There we go. Okay. Let's see. The first operation I want to go over is called conjunction. These all have fancy names, but conjunction is just the and operation. So I'm going to write that like this. A lot of times with operations in programming, you'll see them written in all caps. I'm just going to do that for consistency. So P and Q. And then there's a notation for that that we'll use. And that notation is called a wedge. It is like a symbol that looks like that. So that is the and symbol we're going to use in our class. Different programming languages use different symbols for and. So you might be, familiar with the double ampersand. I don't remember what other ones. Sometimes it's like just a dot. Sometimes you'll see and represented like times, in fact. But for this class, we're going to use that symbol to represent the and operation. So what and means is that both the inputs have to be true in order for the output to be true. So essentially, P and Q requires that both P and Q be true. So this compound proposition, P and Q, is true when P and Q are both true, so I can put true in the first row of my truth table. Now, if either of the two inputs are false, it's going to be false. So when Q is false here, it's false. When P is false but Q is true, it's still false. And when they're both false, it's false. So P and Q outputs a value of true only when both inputs are true. There we go. So the next operation is disjunction. And you can probably guess, disjunction is just a fancy word for or. P or Q. And the notation we'll use for that is called a V. So we've got wedge and V. And so it's that. So let's see. So the way or works in logic is actually an inclusive or. We're going to get to an exclusive or in just a second. but this is an inclusive or. So whenever you see the word or in logic, always assume that it is inclusive, which means that it could be one or the other or both. So that means that even if both of the inputs are true, it's still considered true. As long as at least one of them is true, then the overall disjunction will be true. So that means we have true in the first row, we'll have true in the second row because P is true. In the third row, Q is true, so it's still true. And only when both P and Q are false is the disjunction false. So P or Q is true except when they're both false, in which case it's false. So there we go. So that's disjunction. Now, sometimes when you say A or B, you mean you have to pick one or the other and not both, right? That's called exclusive disjunction. You may hear some drumming in the background. Sorry about that. That's my son, Robin. Exclusive disjunction. So this is sometimes spoken as XOR. So P XOR Q is an exclusive disjunction. And the symbol for that is with like a plus with a circle around it. Like that. So this is exclusive XOR. And it basically says, this is like super salad. When you go to a restaurant, they say super salad, and it's implied like you're supposed to pick one or the other and not both. If you want both, you're going to have to pay extra. So so this is if P is true and Q is false, it's fine, it's true. If Q is true and P is false, it's true. But if they're both true, nuh-uh, no dice. That would be false. So this is the difference. And then, of course, if they're both false, it's false. The difference is only in that first row right there when they're both true. That's going to be false for the exclusive disjunction. So that's XOR. All right, now we're going to use conjunction and disjunction a lot. We won't use exclusive disjunction very much. And another of the most common operations we're going to use is the next one. This one is, in some ways, the most important. It's implication. Implication, also sometimes called a conditional statement. And it is if P, then Q. If P, then Q. And the notation is an arrow to the right. P, if P, then Q. You can also say this P implies Q, and there's a bunch of other ways as well. I'm gonna make a whole video about implication where I go over some more details. But let's just fill out the truth table. If P, then Q. Essentially, this is true. When P is true, it essentially guarantees that Q will be true. That's what this is saying. So if P is true, then Q will be true. So in the first case, when P is true and Q is true, it's true. Now, in the second row, if P is true but Q is false, imagine that's the situation. P is a true statement and Q is a false statement. If I said, if P then Q, then you could actually say, wait a minute, but P is true, however, Q is false. This is saying if P is true, then Q will be true. But if Q is false, that's essentially disproving the claim that the implication is trying to make. So that's the situation in which this is false. Okay, P implies true. Well, if P is true but Q's not, it's false. Now here's the weird part. If P is false, then in fact the statement is true. And that's the case regardless of whether or not Q is true or false. It doesn't matter. So if the P here is false, then you say that's true no matter what. This here, these two cases here, these are referred to as vacuous truth. And I'm going to explain that a little more in a future video. So for now, I just want you to kind of take it on faith for a moment. I will give you a better explanation of why that is the case coming up soon here. But that's called vacuous truth. All right, we have one more of these to go over, and it's biconditional. By the way, these are by no means all of the binary operations that you can do in logic. You can make up other ones, and there are, in fact, others that are common, like NAND and NOR come to mind, but we're not going to discuss those until much later. So, biconditional. All right, so this is like a two-way implication. It's going one way and the other way. So we can write this as P if and only if Q. That's how you write biconditional. P if and only if Q. Now this is actually a common enough phrase in logic and mathematics that it actually has a shorthand, and if and only if, that entire phrase there, can be abbreviated as IFF. If and only if. P if and only if Q. And the notation is a double arrow pointing both directions, like that. Now, essentially, what this means is if P is true, then Q is true, and also if Q is true, then P is true. Okay, I'll also make a separate video kind of detailing how that works. But for now, I want you to understand that biconditional essentially means that P and Q have to have the same truth value. So if P is Q, then true is Q. If Q is true, then P is true. When they're both true, this is true. But if either one of these is false, then it's going to be false, because for the second row here, P is true, but Q is false, then it's false. For the third row, if Q is true, P needs to be true. But in this case, Q is true and P is false, so that's false again. However, in the fourth row, when they're both false, the implication one direction is true vacuously, just like this was, and the implication in the other direction is also true vacuously, because they're both false. So this is true again. Biconditional essentially sets up a situation where this is going to be true exactly when the two inputs have the same truth value, either both true or both false. Okay? That's the way I want you to think about biconditional. It's basically like checking to see if the inputs are the same truth value. Okay, I think that's all I want to talk about in this video. I'm going to bring this truth table back in future videos, so we'll reference it and we'll kind of like make some observations about it and some conclusions coming up soon.